Okay, now I want to kind of change gears a little bit, and I want to talk about refraction a bit more, but now I'm going to take it a step further, and I'm going to talk about dispersion. Now, what I didn't tell you is the index of refraction that I told you earlier, which is how much light speeds up or slows down, is actually going to depend on wavelength, and not all wavelengths are created equally. So suppose I had some air, and I had some glass right over here, and I had some air right over here, then we know that the light's going to bend inwards because we're going from air to glass. However, the red light is going to bend the least, the blue light is going to bend the most, and if we had our Roy G. Bivs, you could convince yourself, the orange, yellow, green, blue, indigo, and violet. So technically violet would bend more, but usually we talk about red and blue because we don't really see a whole lot of violet. Our eyes are not very sensitive to it. So red will always bend the least, blue will always bend the most. Definitely want to know that. Now, if we were to go ahead and look at the index of refraction, as I mentioned, this guy right here is going to be a function of wavelength, and you can kind of see the index of refraction for the blue is going to be larger than the index of refraction for the red, and it's pretty much true for all objects. So right over here, we know that this is going to bend more. Right down here, we're going to bend less, and in general, blue will always bend more than the red will. Now, this is actually the cause of rainbows. It's actually caused by dispersion, and technically it's many many drops of water. We know that we're going to have fast to slow. We know water is going to slow things down. And if we have sunlight, we know sunlight's going to be red and orange and blue and green and indigo and violet. So it's going to be all the colors of the rainbow. And what's going to happen is we can have our red light, and our red light is not going to bend a whole awful lot. So here's my path of my red light, and bada bing, it appears right here. So it does not bend as much. The blue light, on the other hand, is going to bend more because the index of refraction is larger for blue. So there's my blue path, and it's going to come right over here. And here we've separated out my reds and my violets. I said blue earlier, but violet's probably more appropriate. And everywhere in between, we're going to have all the colors of the rainbow. So red, orange, yellow, blue, indigo, violet, kind of working our way from the reds to the violets. Now, I do want to talk about what happens right here a little bit because that is important for rainbow formation. Before I do that, what we do have to say is we always have more than one raindrop, and what we're kind of seeing is we're seeing the compilation of the colors from all of these raindrops. So let me just for a second just talk about two raindrops, but bear in mind it's usually many raindrops. Here we have our sun. And the sun always has to be kind of behind you when you look for a rainbow. You're never going to see it looking into the sun. And what's going to happen is here we have a water drop, and as I said, the red is going to bend the least, the violet's going to bend the most, and we're going to get our red light from this top raindrop right over here. One thing to bear in mind is we're not going to see rainbows all the time. The sun has to be at just the right angle, and the magic numbers are about 40 degrees to 42 degrees. Now, the violet light right over here is actually going to miss our eye, so we're not going to see the rainbow from just one water droplet. You come down a little bit, and we're going to have the red light, not going to bend a whole awful lot. That's going to miss our eye too. However, for this guy right over here, the violet light is going to come right over here, and we're going to see the violet from this raindrop, and all the raindrops in between, we're going to get all the colors of the rainbow. I think that this picture pretty much shows it just a little bit better. We're always going to have the sun kind of behind us, and we're going to have lots and lots and lots of raindrops. The magic numbers, 40 degrees to 42 degrees, give or take. Light comes in, and from the top drop we're going to see the red, and then we're going to see oranges, we're going to see yellows from this guy right over here. We're going to see the greens, we're going to see the blues, we're going to see the indigos, we're going to see the violets from a whole bunch of droplets. Now, let me kind of come back, and I want to talk about that reflection on the back of that raindrop. There's actually a very special angle that's involved for this to happen. And what's going on is we're actually getting this thing called total internal reflection. So let's talk about that a little bit. Suppose I had a flashlight and I was shining a beam like this, and I'll just say that I'm in some water and this is going to be air. This is the case where I'm going from slow to fast. And what's going to happen is light's going to bend away from the normal. And I'll pick this guy right over here. There's my normal line, kind of like this. This would be my angle of incidence. This would be my angle of refraction. And what we're going to say is this guy is going to be larger than what this guy is because I'm going from slow to fast. And you can definitely see it right here. There's my normal line. There's my angle of incidence. There's my angle of refraction. This guy is, again, bigger than what this guy is. You could convince yourself that there's going to be some angle where this ray right here bends and kind of skims along the surface. We actually have a special name for this. We're actually going to call this thing the critical angle, or theta sub c if you wanted to. And this is where it's going to skim along the surface, so there's my critical angle. If I were to shine a light at angles larger than this critical angle, then the light is actually going to reflect backwards because it doesn't have anywhere else to go. So the light's going to come in like this, and it's going to kind of go backwards. Now, I'm probably not telling you anything that you don't already know. We know that if you go to the bottom of a swimming pool and you look up, then you're going to see the trees and telephone lines and stuff like that. But around the edges of the pool, it looks kind of shimmery. What you're seeing is this thing called total internal reflection. You're seeing the bottom of the pool. And what this picture right here kind of shows is it shows a fish, and the fish is going to see the bottom of the pool at some angles larger than the critical angle. So here we have the fish, and the fish is kind of seeing the light that's coming in, seeing trees and telephone lines and stuff like that. But you hit some angle that's larger than the critical angle, what you're going to see is you're going to essentially see the bottom of the pool, the bottom of the pond, or what have you. Any angle larger than this critical angle, and the light is going to bounce backwards, and it's actually called total internal reflection. Now, this actually does have some uses. When we look at a mirror, or when we look at something like that, then what we're seeing is we're seeing a reflection. So this might, right here could be my mirror, and I could say that light would go like this to this. Angle of incidence is the same as angle of reflection and all that good stuff. However, when the light is incident upon that surface, there's going to be some loss, and it's going to heat the mirror up ever so slightly. Total internal reflection, on the other hand, is going to reflect 100% of it. And we actually take advantage of this in many optical instruments. We don't like to lose light. That's a bad thing. So optical instruments tend to use prisms, and they use total internal reflection. What we can do is we could then lengthen a path between lenses in something like binoculars. So if you look inside of binoculars, they don't use mirrors to lengthen the path. We have light kind of coming in, and the light's going to come in. It's going to totally internally reflect here, totally internally reflect here, kind of come down, totally internal reflect, totally internal reflect, and then go up to the eyepiece. So it's taking this path right over here. It makes it a little bit longer, and that's going to make the image better able to be focused. So we want to have a longer path length, but we don't want to lose our light. So we actually have uses for this. Other uses would be fiber optics. With fiber optics, what we could have is we could have this fiber like this, and it's going to rely on total internal reflection in order for it to kind of work. What the optical fiber kind of is you can kind of think of it like a light pipe, if you will. And it's pretty much going to do the same thing as these binoculars. We're going to put some light into one end, it's going to come out the other end, and it's going to bounce around. So picture for a second, I'm going to exaggerate this guy right over here. Here's my optical fiber, and if I shine some light in right here, it's going to have total internal reflection here, right here, right here, right here, right here, right here, right here, and then it's going to bounce out the other end. Again, we're not going to have any loss right over there here, so no loss. What this means is we're not going to have to waste any energy, and if we were to talk about optical fiber in the language of internet, it's screaming fast. The reason why it's screaming fast is because we're traveling at the speed of light, or nearly the speed of light. Going through copper phone lines for DSL tends to be slower. So when you move to a big city and you get Fios, highly recommend it. That is screaming fast. Back in the 80s, they turned these things into lights, but now we have better uses for them. So this kind of brings us back to rainbows, and I said the angle kind of mattered. What we needed the angle for was we needed the angle for that total internal reflection. So the light kind of came in, it spread out, the reds and the violets, not going to draw that for you. And we had the light kind of come like this. We had to have the total internal reflection back here. Just kind of some other rainbow facts. What we're going to see is we're just going to see a single color from each drop, kind of showed you that. The rainbow you see is going to be slightly different than everybody else, so it's kind of unique to you, and it's going to move with you. Something that's also interesting is inside of the rainbow, it's always just a little bit brighter. And you can kind of see this in this image right over here. Right here it's going to be relatively bright. Right here it's going to be a little bit darker. We can also see a secondary rainbow, and it's actually going to be a little bit fainter. What's going on with that is there's actually two internal reflections, and there's some light lost inside of the water. It's always reversed in color, so you can hopefully see it. Right here is the secondary rainbow. Let's kind of talk about that. It's always going to be larger. Here's my standard, ordinary, everyday rainbow. I've talked about that. The secondary rainbow is actually going to be a little bit higher, and these guys I said are around 40 degrees. These guys are around 50 degrees, so they're higher in the sky. The light's going to come in, and it's going to spread out. The blue is going to bend a lot. The red's not going to bend nearly as much. We're going to have a total internal reflection here, and then it's going to come out. It's going to bend outwards, and we're going to have our rainbow right over here. You can kind of see there's my violet and there's my red, and because of this second reflection, it flips those guys around. So now there's my red, there's my violet, and that's why the secondary rainbow is always has the colors reversed.